Hi, welcome back to the Journey of Stars. I'm your tour guide, Luna. In the last episode, we talked about what determines the color of a star, why blue stars are hotter, red stars are cooler, and the standard MK spectral classification system. Now we know that temperature explains the color of a star. But what about what a star is made of? Now let's have a closer look. In fact, we can use the spectral lines to determine chemical composition of a star. Each chemical element produces a unique set of pattern when it absorbs or emits light. When an atom is being heated up, the atom absorbs that certain level of energy and produces a fixed absorption line pattern. All the little particles in the universe try to stay in its lowest energy level. As a result, since it wants to get rid of the extra burden, it emits light back to the universe with a pattern that is similar to the absorption lines, with the colored and dark parts reversed. This is because electrons in every atom has distinct energy level. Each has a unique set of amount of energy to get excited due to its distinct structure. This feature leads to the phenomenon that each chemical element, ion or molecule, has a unique set of energy levels. When a star emits light, we use a spectrometer to observe the spectral lines in them. Each set of lines indicates a particular chemical element, with the line strength indicating the abundance of it. These fingerprints can be compared to the previously collected fingerprints of atoms and molecules, and are thus used to identify the atomic and molecular components of stars and planets. By analyzing the chemical composition of a star, we can speculate their size and stage of evolution. And how does temperature of a star relate to its luminosity? Don't get confused here. Luminosity, or absolute brightness, is a measure of how much energy a star can emit per unit time. It is different than the term brightness, which can be affected by the observer's distance to the object. Here, I want to introduce a super powerful tool in astronomy. If you only take one thing away from today's lecture, this is the part you want to pay close attention to. So, ladies and gentlemen, let's welcome the very famous HR diagram. This relationship is discovered by the two astronomers Herström and Russell. After plotting a lot of star surface temperature with their luminosities, they discovered a pattern. The stars do not just line up randomly in space. They line up on a couple different linear sequences, and most of them sit on the central region, which is the main sequence. Here, we can see most stars lie along the main sequence according to their mass. On the top right is a red giant and supergiants branch with brighter stars, and on the bottom left is a white dwarf region of stars much dimmer. This diagram is essential for our understanding of stellar structure in evolution. So, what is a main sequence star? Why most stars are undergoing that stage of life, and what is their destiny? That, my fellow stellar adventurers, are exactly what we will explore in the next episode. Thank you for watching episode 3, part 2 of my series of astronomy, The Journey of Stars. Today we learned about how to use spectral lines to identify the chemical composition of a star, and how the HR diagrams connects a star's luminosity with its temperature, and draws the general pattern of stellar evolution. This episode is produced by me, along with my project instructor, Mr. Decorado. If you want to learn more about what a main sequence star is and probe the destiny of our sun, please subscribe to my channel and follow the coming episodes. Enjoy your day, and don't forget to keep looking up to the stars.